Hello. Hi everyone, welcome back to my channel. I don't know why I said that. Anyways, this is a paper 1 overview, physics topics 1 to 4. It's got triple content in it as well, which I didn't mean to do, but it has, so I hope you are all happy with that. I don't think it covers absolutely everything, so I don't use this as Bible. However, it does have most things, so let's just get into the video. What are energy stores? A system is an object or group of objects. When a system changes, the way energy is stored also changes. Examples of energy stores are a ball rolling and hitting the wall. The system is the moving ball. When it hits the wall, some of the kinetic energy is transferred as sound. Another example would be a vehicle slowing down. That didn't go very slow. The system is the moving vehicle, and when it slows down, kinetic transfers to thermal due to friction between the wheels and the brakes. So how do you calculate energy? So kinetic energy is calculated through mass, speed, velocity, and just this kinetic energy itself. So do you know the equation already? If so, you have 2 seconds. Tell me 1, 2, and oh, it's that. So the formula for kinetic energy is half times mass times velocity squared. So this is, I think it might be on the equation sheet, so I guess it doesn't matter that much, but it's important to know how to apply it. Next up, we got elastic potential energy, which is the type of energy stored in a spring when it is stretched. So here are the units, joules, newtons per meter, and meter extension, blah, 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 blah. There we go, there he is again. Can you guess how you arrange this? You have 2 seconds. 1, 2, gone. Where is it? There it is. So elastic potential energy equals half times kinetic energy. Half times spring constant times extension squared. So that is also useful to just know, even though it might be on your sheet. Next up, we got gravitational potential energy. So GPE, gravitational potential energy, is measured in joules, and gravitational field strength is measured in. This is important to know because they're not going to tell you this. Well, they might. If they don't tell you, then always assume that the gravitational field strength is 9.8, because that is the gravitational field strength of the Earth. Unless it specifically tells you the gravitational field strength is 10 or like 9 or 11, because you might be on a different planet, or they might want you to like generally say, then just always assume that it's 9.8 newtons per kilogram. And then we have height in meters and mass in kilograms. So another tip, if you're doing this ever, these are the standard units, and if you don't get the question given to you with these units, say you get grams or centimeters, you want to convert them to these units. So there we go. I didn't give you time to guess, so here it is. Gravitational potential energy is just mgh, m times g times g times h, mass times gravitational field strength times height, and yeah, so that's useful to know as well, even if it does give it to you on the sheet. Now we have specific heat capacity, which is the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 K. What's 1 K? I don't actually know. So just go with 1 degree Celsius. There he is, doing his little spin. That's vector, if you didn't know. Anyways, here's the formula. So I don't know why it's arranged like this, but you can just rearrange it. It is mass times specific heat capacity. Oh, sorry. mass times specific heat capacity times temperature change, and it gives all the units here, and then that's heat. So if you want to rearrange, obviously you just do what you would do when you're rearranging, because I can assume you can do mass. No, here we are onto calculating power. So power is defined at the rate in which energy is transferred or the rate at which work is done. So you can also, yeah. So you can guess how you arrange this. These are units once again. 3, 2, 1, and there he is. There it is. So power equals work done over time. Also, if given two motors, A and B, the motor that can do the same work faster is more powerful, as the energy is transferred at a faster rate. So speed is also considered when thinking about power. Energy transfers. Energy can be transferred usefully, stored or dissipated, but it cannot be created or destroyed. So that is very important. Energy can't be created or destroyed. Remember, you don't want to be saying things like energy is created by this or energy is destroyed by this or whatever. You don't want to speak like that. Energy, it just can't. It's just not. It doesn't work like that. So you want to use words like transferred and dissipate. In all system changes, energy is dissipated. So that is stored in less useful ways. This energy is often described as being wasted. So, for example, thermal energy is often created. No, not created. Sorry. Thermal energy is often a result of, let's say, like a motor running. Obviously, the kinetic energy is the main energy store, but it's also dissipating thermal energy because it gets hot. Oh, there he is with his little gun. So, reducing energy waste. There are many ways you can, not many, that's over exaggeration. There are a couple ways you can reduce energy waste. So, sorry. So, first up, we've got lubrication. And no, I don't mean that strangely, so hold your horses. So, which could be oil in a motor, which in turn reduces friction, so less energy is lost as heat, thermal energy, through friction. Not lost as in destroyed, lost as in dissipated. So thermal insulation is another one. Double glazing. Once again, just don't be weird, please. That's not what I mean. But double glazing is less useful thermal energy lost, which is through windows, as will be seen in a second. See, look, this is a double glazed window. You might see them at churches. I know at my church we got a lot of double glazed windows because it gets very cold in churches. So that's the glass. That's another set of glass, and that's the airspace between the two. Thermal conductivity. The higher the thermal conductivity of a material, heat is allowed to travel through the material more easily. I don't know if that's correct phrasing. So the higher the rate of energy transfer by conduction across the material. Thermal conductivity in a building. Rate of cooling is low if walls are thick and thermal conductivity of the walls are low. So if the walls are thin, metal sheets, heat will be lost very quickly. Efficiency. The efficiency is the ratio of the useful work done by a machine, engine, device, etc. to the energy supplied to it, often expressed as a percentage. So the formula for efficiency is useful energy output over total energy output. I'm not sure if they give it to you on your equation sheet, but it's always good to know these things in case. So the efficiency of a system can be increased by, as I said before, reducing waste output through lubrication, thermal insulation, etc., and recycling waste output through absorbing thermal waste and recycling as input energy. Energy resources. So there's vector again. Anyways, renewable energy is energy which can be replenished as it is used. For example, wind will never stop. Non-renewable energy is energy which cannot be replaced and can only be used the one time. Renewable energy sources include biofuel, wind, hydroelectricity, geothermal, tidal, solar, waterways. These are all very important because you're going to want to know these for the exam because it might ask you about any of these. So your non-renewables are much less, so very easy to remember the non-renewables. Fossil fuels are like coal, oil and gas, and then nuclear fuel. Non-renewable energy is used for more large-scale energy supplies due to the large energy output per kilogram of fuel. Renewable resources cannot provide such a large amount of energy as easily. So non-renewable resources are seen as more reliable, obviously because they've been used for so many years, and thus we know it's going to work better. However, renewable energy has become more important due to the finite lifetime of fossil fuels, and so the development has become more important. Renewable energy is not always the most reliable, as I said before, as solar doesn't work in bad weather or at night, and wind is only intermittent. However, coal, oil and gas is never going to have any issues, really. Also, we know that fossil fuels, it's more important to be using renewable energy, as we know that fossil fuels are finite, they're running out. It takes millions of years really to create a fossil fuel. That's how they've been created over the years, and so it's not very easy to make one. So energy resources, main energy uses: transport, heating, electricity generation, there we go, environmental impact. Is he the environment? Okay. Fossil fuels involve destroying landscapes. Wind turbines can be considered an eyesore. So those are some complaints about energy being transferred, generated. Use of energy sources. Fossil fuels release harmful emissions. Solar, wind, solar and wind directly create electricity with no emissions. Sorry, I just couldn't read that properly. Okay, we're on to topic 2, electricity. So circuit symbols. There's young Sheldon, because I'm going with the physics theme, like people in physics. Anyways, not like you care. So some circuit symbols. We'll play a little guessing game. I'll give you 2 seconds for each one. 1, 2, bow. That's an open switch. These are important to know, by the way, because it might ask you, put a switch on this circuit, put a diode on the circuit. Anyways. Okay, what's this? 3, 2, switch, close. What's this? 1, 2, cell. What's this? 1, 2, battery. What's this? 1, 2, diode. What is this? 1, 2, resistor. What's this? 1, 2, variable resistor, See, this is a regular resistor. And then this is a variable resistor. So that's kind of a line indicating that the variable will affect it. So what's this? 1, 2, LED. Like you might have in your room. I have them in my room, but they overheat and they cause bugs. But that's okay, you don't care about that. Anyways, so we can see this is light. It's like a light emitting diode. So that's a diode symbol. And then that's the light being emitted. 1, 2, lamp or bulb. If you said bulb or filament lamp, I'm pretty sure, then you'll be correct. What's this? 1, 2. No, it is not a form of resistor. This is a fuse, so line directly through it means it is a fuse. Don't forget that. 1, 2, voltmeter. You should have got this because obviously V for volt. 1, 2, ammeter, A gram meter. 1, 2. Thermistor, of course, is a form of resistor. This is to indicate the thermistness of the 1, 2. Light dependent resistor, LDR. See, that's the light going into it because it's dependent on the light. Okay, circuit symbol. Electrical charge. For charge to flow, there must be closed, no open switches. There must be a source of potential difference, battery or cell. I don't think he's politically acceptable anymore, so I'm sorry if he troubles you. Circuit symbols. I don't know why I keep saying the title, my bad. Electrical current. Current is the flow of electrical charge. The greater the flow of charge, the greater the current. So Q is charge flow, I is current, and time is time. T is time. So, I don't know why I'm doing a little flip. Guess how you would arrange that. 3, 2, 1, and this is how you would. So, charge, flow, current, and time, all arranged like this. Oh, sorry, go back a bit. And these are your units. In a single loop, closed loop, the current has the same value at any point. The current I through a component depends on both the resistance of the component and the potential difference V across the components. The greater the resistance of the component, the smaller the current for a given potential difference across the component. That is scary. Resistors. If the resistance is constant, an ohmic conductor current is directly proportional to the potential difference. In this case, the graph is linear. If the resistance of components such as lamps, diodes, thermistors, and LDRs is not constant, it changes with the current through the component, so the graph is non-linear. For example, the resistance of a filament lamp increases as the temperature of the filament increases, and the current through a diode flows in one direction only, so it has a higher resistance in the reverse direction. So you're going to want to know what the resistors are titled. So this is a resistor at a constant temperature. I don't know if resistor is spelled right. Constant temperature obviously is constant here, we know. This is a filament lamp, and this is a diode. How does the resistance change with current? As current increases, electrons, charge, has more energy. Where when electrons flow through a resistor, they collide with the atoms in the resistor. This transfers energy to the atoms, causing them to vibrate more. This makes it more difficult for electrons to flow through the resistor. So resistance increases and current decreases. With temperature, resistance changes. As normal wires, the same process occurs as atoms vibrate when hot. Thermistor, in hotter temperatures, the resistance is lowered, and these are often used in temperature detectors, thermostats. How does the resistance change with length? The greater the length, the more the resistance, and the lower the current. Electrons have to make their way through more resistor atoms, and thus it is harder than using a shorter wire. How does the resistance change with light? LDRs, light-dependent resistors. The greater the intensity of light, the lower the resistance. So the resistance is greatest when it is dark. These are used in automatic night lights. How does the resistance change with voltage? Diodes. Diodes allow current to flow freely in one direction. In the opposite direction, it has a very high resistance, so no current can flow. Domestic uses and safety. Mains. So mains electricity is an AC supply. In the United Kingdom, the domestic electricity supply has a frequency of 50 Hz and is about 230 volts. So you're going to want to know that, as it might ask you a question about it. So remember, domestic electricity supply frequency 50 Hz and 230 volts. AC is alternating current, which comes from the mains. Current continuously varies from positive to negative. Charge changes direction. DC, direct current, is the movement of charge in one direction only. Cells and batteries supply direct current. Cabling in a plug, there are 3 wires, so this is important to know generally, and also for physics. So the live wire, brown, at 230 volts, as I said before, carries the alternating potential difference from the supply. This may be dangerous even if main circuit is off, as current may be still flowing through it. So I don't know, my teacher told me back in the day something like it's the live wire and it's brown because if you touch it, your pants will go brown. You can infer that you will die and you will excrete in your underwear. I don't know why she said that, and I don't know why I'm saying that. So I guess it would just help you remember that the live wire is dangerous and it carries the alternating potential difference from the supply. Okay, the neutral wire. Blue at 0 volts, it completes the circuit, so it's just used to complete the circuit. The earth wire, so this one's very important, thus there is so much yap about it. So it's got green and yellow stripes. I think I can see, never mind. Green and yellow stripes at 0 volts, it only carries a current if there is a fault. Safety wire to stop the appliance becoming live. If it is connected to the earth and to the casing. If the live wire touches the metal casing of the appliance, it will become live. You'll get a serious electric shock if you touch it, as a current flows through to the ground. So, there's 3 points of a plug in the UK, and the earth wire, the top one is connected, and it's as it says here, it acts as a safety wire. So you see that little part at the top of your plug, that is for safety, as the 2 other ones are used for actually channeling the electricity. So other things about this cable is this is the outer insulation of it. Obviously the outside of the cable itself, if you get what I'm talking about, sometimes when your charger or your earphones get frayed, you can see the wires in them rather than being covered. And there's the cable grip. Power is the energy transferred per second. It is directly proportional to current and voltage. Power loss is proportional to resistance and the square of the current. Energy is transferred from chemical potential in batteries to electrical energy in wires to any form of useful energy in the devices they power. To calculate energy transferred, you should do energy transferred, joules, charge, potential difference in this form, or energy transferred is power times time. So these 2 different ones in case you want to calculate energy transferred and your variables are charge and potential difference, or if they're power and time. So energy transfers in everyday appliances. Electrical energy may be transferred by the appliance in different ways. Kinetic energy for a motor, thermal energy in a kettle. Work done is when charge flows through a circuit and is also equal to energy transferred, as all the electrical energy ideally gets transferred to the appliance. Power rating of an appliance shows the power it uses in watts. So a greater power rating means it uses more energy. Series and parallel circuits. So series circuits. Here is a series circuit or single circuit, as they're called. It's a closed circuit. Current only follows a single path, as we can see, just one path. The current is the same everywhere, 0.5, 0.5. Total resistance is, I don't actually know what that means. So parallel circuits, as we can see, there's another layer compared to here. It's a branch circuit. Current splits into multiple paths. Total current into a junction equals total current in each of the branches. The same potential difference is the same across each branch. So series circuits, components are connected end to end. All the current flows through all the components. You can only switch them all off at once. Potential difference is shared across the whole circuit. Current is the same through all parts of the circuit. Total resistance is the sum of the resistance in each component, and resistance of two components is bigger than just one of them, because the charge has to push through both of them when flowing around the circuit. Parallel circuits, so components are connected separately to the power supply. Current flows through each one separately. You can switch each component off individually. Potential difference is the same across all branches. Because charge can only pass through any one branch, current is shared between each of the branches. Total resistance is less than the branch with the smallest resistance. Two resistors in parallel will have a smaller overall resistance than just one. And because charge has more than one branch to take, so only some charge will flow along each branch. The national grid is a system of cables and transformers linking power stations to consumers across the UK. Electrical power is transferred from power stations to consumers using the national grid. So these are the transformers. These change potential difference. So step-up transformers increase the potential difference from the power station to the national grid. So as the power is constant, P equals IV, current decreases, so less energy is lost. So as you can see, power station here, step-up transformer, high voltage transmission lines, and then a step-down transformer will decrease the potential difference from the national grid to the consumers for consumer safety. So in homes, factory shops, the general process is from the power station, the transformers step it up, goes through the high voltage transmission lines, and then goes through onto the step-down transformers to your homes. Charge, a property of all matter. Positive and negative charges exist. If a body has the same amount of positive and negative charge, they cancel out, forming a neutral body, i.e. protons and electrons in a neutral atom. Like charges repel. Opposite charges attract, and insulators do not conduct electricity. Their electrons cannot flow through the material, they are fixed. Conductors can conduct electricity. Their electrons can flow and are not fixed. They are delocalized. So it's a bit of chemistry coming through. I don't know why I can go past that. So static electricity, when two insulators are rubbed together, electrons are transferred from one object to the other, forming a positive charge on one object and a negative charge on the other. If conductors were rubbed, electrons will flow in and out of them, cancelling out any effect, so they will stay neutral. Insulators become charged because the electrons cannot flow. A positive static charge forms on object which loses electrons. A positive static charge forms on object which loses electrons. A negative static charge forms on object which gains electrons. Which object loses or gains electrons depends on the materials involved. Sparking occurs when the charge builds up and the objects are close, but the spark, is when the charge jumps through the air, from the highly negative object to the highly positive object to balance out the charges. The charged objects experience a force, electrostatic force of attraction or repulsion. The greater charge equals greater force. A more positive object means a more negative object. Closer together means a greater force. Force is proportional to the inverse square of the distance, and it is a non-contact force, as force can be felt even when the objects are not touching. So, like magnetic fields for magnets, electric fields are for charges. They point in the direction a positive charge would go, i.e. away from positive charges and towards negative charges. They point to charges at right angles to the surface. The stronger the charge, the more field lines present, and the stronger the force felt. Closer to the charge, the stronger the force felt. So here, yep, there's young Sheldon. Oh, sorry. Okay, on to topic 3, particle model of matter. So density, the density is defined as the mass per unit volume. P equals density, M equals mass, and P equals volume. So here are the units: kilograms per meter cubed, kilograms and meters cubed. So density equals mass over volume. Density depends on the spacing of the atoms in matter. Solids and liquids have similar densities as the space between the particles does not change significantly. Usually liquids have lower density than solids. The main exception is ice and water. So here's a solid structure, here's a liquid structure, mainly compact between the two, but here they have a rigid, unmoving structure, and here the particles have some room to move around a little. Gases have a far lower density. The spacing between atoms increased times 10 as the particles have lots of energy to move. So volume increases greatly, and therefore the density decreases greatly compared to solids and liquids. Remember, if questions involve change in state and ask for new volume or pressure, then the mass is the same. So here you can see the gas, there is so much space for the particles to move around, and there is no rigid structure, unlike these two. Mass is conserved during a change of state. If 20 grams of liquid evaporates, the gas produced will also weigh 20 grams. So here is the little chart for it. So a solid to a gas is called sublimation. A solid to a liquid is melting, and then a liquid to a gas is evaporating. So these are kind of basic. I think most people know. This is just common knowledge. So a gas to a liquid is called condensing, and then a liquid to a solid is called freezing, and there's no really jump from gas to solid. These physical changes are reversible and not chemical changes. They are not chemical because the material retains its original properties when reversed. So example, an egg is a chemical change, as you can boil an egg, you can scramble an egg, but you can't put it back in the shell. You can't make it back to its original egg-like form. So change of state, internal energy. Energy which is stored by particles, atoms, and molecules within a system. The energy takes the form of kinetic energy, vibration of atoms, etc., and potential energy between the particles. Oh, that was fun to watch. I'll do that one again. Ooh. So heating a system. Heating increases the energy the particles have. This increases the internal energy. This either raises the temperature of the system or produces a change of state. Specific heat capacity. The amount of energy required to raise the temperature of 1 kilogram of subject by 1 degree Celsius, as said in topic 1. So I think here is a easier formula for you guys. Sorry, it's hurting my eyes to look at. So triangle E is change, which is the triangle, in thermal energy, which is measured in joules, which equals the mass, kilograms, times by the specific heat capacity, C, joules per kilogram per degree Celsius. No, joules per kilogram to the power of -1 per degree Celsius to the power of -1. And then times by temperature change. So triangle for change and then temperature. So once again, if you want the specific heat capacity, you can rearrange, or you can just, if you want any of these, you can rearrange. Here is the formula. So specific latent heat, the amount of energy needed to change the state of 1 kilogram of a substance without a change in temperature. The substance needs to be at the right temperature to change state first. So specific latent heat of fusion is energy to melt or freeze, and specific latent heat of vaporization is specific latent heat of vaporization is energy to boil or to condense. So energy for a change of state in joules equals mass times specific latent heat. Once again, you can rearrange. Okay, energy is absorbed when melting and evaporating, and energy is released when freezing and condensing. Sublimation is when solid goes straight to gas, dry ice, for example. Solid CO2 does this. So as I said a couple slides ago, but there isn't a gas to a solid form. So temperature changes, once again, specifically the heat. At A, it is solid. At B, it reaches 0 degrees. From B to C, there is no temperature change because the energy is used through melting. And from C to D, it is a liquid state. From D to E, the water is boiling. This takes longer because the evaporation takes more energy. And from E to F, the gas is heating. So you want to remember generally how this looks, this table here. Pressure. The molecules of gas are in constant random motion. The temperature of the gas is related to the average kinetic energy of the molecules. The higher the temperature, the greater the average kinetic energy, and so the faster the average speed of the molecules. When the molecules collide with the wall of their container, they exert a force on the wall. The total force exerted by all the molecules inside the container of a unit area of the walls is the gas pressure. Changing the temperature of a gas held at a constant volume changes the pressure exerted by the gas, known as the pressure law. Changing the volume of a gas affects the pressure. A gas can be compressed or expanded by pressure changes. The pressure produces a net force at right angles to the wall of the gas container, or any surface. Increasing the volume at which gas is contained at constant temperature can lead to decrease in pressure, known as Boyle's law. This is due to the reduced number of collisions per unit area. So for a gas at a fixed mass and temperature, pressure volume equals constant. Increasing the pressure of a gas. Doing work on a gas increases the temperature. So work done equals force times distance, which also equals force over area times distance, which also equals pressure times volume. So simply, work done is pressure times volume. Doing work on a gas means compressing or expanding the gas, so changing the volume. Pumping more gas in the same volume means more particles are present, so more collisions occur per unit time with the walls, so pressure increases. Energy is transferred to the particles when more gas is added into the fixed volume, so this heats the gas. The particles collide with the wall, which is moving inward. So the particles gain momentum as the rebound velocity is is greater than the approaching velocity. So as the particle has a greater velocity, the pressure increases as the particles collide with the walls more frequently. Time between the collisions decrease. And the temperature also increases as the kinetic energy of each particle increases. Oh, that really hurt my eyes. They just become very bright now. Atomic structure, topic 4. We're on to topic 4 now. So, positively charged nucleus, which contains neutrons and protons, surrounded by negatively charged electrons. That is atomic structure. The structure of an atom. So, these are important to know and memorize. So, if you already know these, then that's a great head start. Let's see what they are. So, a proton relative mass is 1, a neutron's relative mass is 1 as well, and then electrons is 0, or more specifically 0.0005. So the relative charge is +1 for a proton, 0 for a neutron, and then -1 for an electron. The typical radius of an atom is 1 × 10 to the -10 meters, and the radius of the nucleus is 10,000 times smaller. Nearly all of the mass of the atom is concentrated at the nucleus. So electron arrangement. Electrons lie at different distances from the nucleus. So if you've done your chemistry paper 1 and you did well on that, then you would know about electron arrangement and atomic structure. So electrons lie at different distances from the nucleus, different energy levels. The electron arrangements may change with the interaction with the electromagnetic radiation. Isotopes and elements. All atoms of the same element have the same number of protons. Neutral atoms have the same number of electrons and protons. Isotopes are atoms of the same element but with different masses, which have the same number of protons but different number of neutrons. For example, carbon-12, carbon-13, and carbon-14. So this is important to know, as you may be asked. A question regarding this, so X is the letter of the element, A is the mass number, and Z is the proton number. Where N is the charge, so it's either a positive charge or a negative charge. On a normal neutral atom, electrons equal protons, so it cancels out. However, if N has more electrons than protons, then negative N charge. If N has fewer electrons than protons, then plus N charge. The number of protons does not change for a certain element. When electrons change orbit, move closer or further from the nucleus, when electrons move to a higher orbit further from the nucleus, the atom has absorbed electromagnetic radiation. When the electrons fall to a lower orbit, closer to the nucleus, the atoms have emitted electromagnetic radiation. If an electron gains enough energy, it can leave the atom to form a positive ion. How and why the atomic model has changed over time. So this is also important for your history of an atom in chemistry, which you've probably already done. In 1800, Dalton said everything was made of tiny spheres, atoms that could not be divided. Then in 1897, J.J. Thomson discovered the electrons, and the plum pudding model was formed. So as we can see, plum pudding has like plums distributed around it, and so we can see that the negative electrons are distributed around a sphere of positive charge. The overall charge of the atom is neutral, so the negative electrons will disperse through the positive pudding to cancel out the changes. How and why the atomic model has changed over time is still the title. In 1911, Rutherford realized most of the atom was empty space, so the gold foil experiment is important to know. Most alpha particles went straight through, so most of the atom is empty space. Some alpha particles were slightly deflected, so nucleus must be charged by deflecting a positive Alpha. Few alpha particles were deflected by the 90-degree angle, so nucleus contained most of the mass. The 1911 Rutherford model, which he created after his experiment. So now there is a positive nucleus at the center of the atom, and negative electrons existing in a cloud around the nucleus. But we know that isn't right, as in 1913 Bohr produced the final model of the atom. If Rutherford was right, the electrons in the cloud close to the nucleus would get attracted and cause the atoms to collapse. So now the electrons exist in fixed orbitals. Later on, the positive charge of a nucleus could be subdivided into smaller particles, each with the same amount of charge. The proton, 20 years after the nucleus was an accepted scientific idea, James Chadwick provided evidence to prove neutrons existed. So radiation. Some atomic nuclei are unstable. The nucleus gives out radiation as it changes to become more stable. This is a random process called radioactive decay. Activity is the rate at which a source of unstable nuclei decays. So a sample with high activity has a fast rate of decay, measured in becquerels, BQ. Count rate is the number of decays recorded by a detector per second. For example, a Geiger-Müller tube, sorry if I pronounced that wrong. So some forms of decay, we have alpha decay from a helium nucleus. It's highly ionizing, weakly penetrating, however, it can only go through 5 centimeters of air. Yeah. So beta minus electron, medium ionizing and medium penetration, so it's like the middle ground. It can go through 50 centimeters of air and a sheet of paper. Sorry, I'm a bit tired. So gamma radiation is low ionizing, however it's highly penetrating, can go very far in the air, and few centimeters of lead. So nuclear equations are used to represent radioactive decay. We can see here, which represents like the X we were looking at earlier. The emission of the different types of nuclear radiation may cause a change in the mass or the charge of the nucleus. So this is how you would like calculate. So alpha decay causes both the mass and the charge of the nucleus to decrease. So beta decay is here, different to how you could calculate alpha decay. It does not change the mass of the nucleus, however it does cause the change So beta decay does not cause the mass of the nucleus to change, but does cause the charge of the nucleus to increase. Gamma decay, it does not cause the mass or charge to change. So half-life, this is important to know as a question will probably come up on it. And you'll probably be asked, I'm sorry, I'm so tired. You'll probably be asked how to calculate half-life. So the half-life of an isotope is the time taken for the half of the nuclei in a sample to decay, or the time taken for the activity or count rate of a sample to decay by half. It cannot be predicted when any one nucleus will decay, but the half-life is constant that enables the activity of a very large number of nuclei to be predicted during the decay. So if 80 atoms falls to 20 over 10 minutes, the half-life is 80 divided by 2, which equals 40, and then another 40 divided by 2 is 20. So 2 half-lives in 10 minutes, so half-life is 5 minutes. A short half-life. This source presents less of a risk and does not remain strongly radioactive. This means initially it is very radioactive, but quickly dies down, so presents less of a long-term risk. A long half-life. The source remains weakly radioactive after a long period of time. Americium has a half-life of 432 years. It is an alpha emitter and used in smoke alarms. It is emitted into the air around the alarm, and it does not reach far because alpha is weakly penetrating. If smoke reaches the alarm, the amount of alpha particles in the surrounding air drop. This causes the alarm to sound. It is suitable because it will not need to be replenished, and its weak activity means it won't be harmful to anyone. So this is the number of atoms that go down over time. Calculating the ratio of net decline of radioactive nuclei after X half-lives. Half the initial number of nuclei, keep doing so X number of times. So net decline equals initial number, take away number after X lives over initial number. Radiation and contamination. So contamination lasts for a long period of time. The source of the radiation is transferred to an object, and radioactive contamination is the unwanted presence of radioactive atoms on other materials. The hazard is the decaying of the contaminated atoms or releasing radiation. For example, radioactive dust settling on your skin will become contaminated. Irradiation lasts only for a short period of time. The source emits radiation which reaches the object, exposing an object to nuclear radiation, but does not make it radioactive. For example, radioactive dust emitting beta radiation which irradiates your skin. Medical items are irradiated sometimes to kill bacteria on its surface, but not to make the medical tools themselves radioactive. Scientific reports published need to be peer-reviewed. If they are on the effects of radiation on humans, peer review is essential. If humans got measurements wrong, if initial studies got measurements wrong, safety levels based on the study may cause people to die. Radiation, background radiation, weak radiation that can be detected from natural or external sources, so cosmic rays, radiation from underground rocks, nuclear fallout, and medical rays. That might be important, as I saw that come up on my test before. The level of background radiation and the radiation dose may be affected by occupation and or location. The measurement of radio dose is in cieverts, which is SV. So more uses: tracers. Technetium is used as a medical tracer. Half-life of 6 years. Decays into a safe isotope that can be excreted by the body. It is injected or swallowed, and thus there is enough time for it to flow through the body and be detected before it decays away, but only presented for a short enough time to minimize any form of radiation. It is a gamma emitter, so it can pass through the body tissue without being absorbed, as it is the most penetrating. So more uses is it can be used in chemotherapy. Gamma emitters are used to emit gamma rays, which are directed onto certain areas of the body with cancerous cells, which absorb the energy and die, controlling the disease. It is used to control any other unwanted tissue too. However, it is hard to direct accurately. Surrounding healthy cells may also be irradiated, and their destruction causes unhealthy side effects. So nuclear fission, I'm pretty sure this is a triple topic, so if you're not triple, I don't think you have to pay any mind to this, but I'll go over it. So nuclear fission is the splitting of large and unstable nucleus. For example, uranium or plutonium. Spontaneous fission is rare. Usually for fission to occur, the unstable nucleus must first absorb a neutron. When the unstable nuclei absorbs a neutron, it splits into two smaller nuclei, roughly equal in size, and then it emits 2 or 3 neutrons and gamma rays. Energy is released by the fission reaction. This neutron may collide with another radioactive nucleus. This nucleus absorbs the neutron and it becomes unstable. The nucleus splits, releasing another neutron, and produces more energy. This is a chain reaction as energy is being released, and one split causes another to occur. A neutron needs to be absorbed initially before it splits, because it needs a little extra energy before it can split and release lots of energy, like a ramp on a cliff. The neutron gives it enough of a kick to get over the ramp to fall. After the nucleus splits, it leaves the 2 smaller nuclei roughly equal in size, and they both, along with the neutrons, have kinetic energy. If the chain reaction is not controlled, it will increase at an exponential rate, which is what happens in a nuclear weapon. This process is used in nuclear fission with uranium nuclei. So nuclear fusion is when two small nuclei fuse to form a heavier nucleus, releasing lots of energy. The sum of the masses of the two nuclei is more than the mass of the heavier nucleus. Some of the mass is converted into energy, released as radiation. The sun is a natural fusion reactor. Fusion would be a much more efficient way of producing energy compared to fission. However, no design has been produced that could accomplish positive net energy on Earth. There we go, we're done. Oh, sorry I got a bit tired at the end. I hope that was useful to you. I know some of it was babble and waffle, but it is key that you know a lot of that information. It's just like a last minute overview of the topics covered in less than an hour, so that's pretty good. Thank you so much for watching, everyone. If you have enjoyed and it was helpful, make sure to like, subscribe, hit that bell, and etc. You know, leave a comment, tell me how you liked it. And I'm so sorry for that choice of emoji at the end of the video. It must be highly disturbing to witness. I hope you liked the little graphics I had throughout the video. You know, normally I just have a boring PowerPoint, but yeah. So let me know if I got anything wrong. Let me know if it was helpful, like I just said. And thank you so much for watching. Have a lovely day. Bye!